The BYU 2023 Mars Rover team has improved our design from past years to create a rover that can excel at competition missions while meeting design requirements at this year's University Rover Challenge. The rover's legs have a rocker bogie design with a joint allowing them to fold up and down while fitting within the 1.2 meter cubed size requirement. The legs and chassis are made using aluminum, while the arm utilizes carbon fiber tubing to ensure the rover remains lightweight and capable of accomplishing difficult tasks. Through our optimization, the rover remains under 50 kilograms in any configuration and under 70 kilograms total. Power for the rover comes from an integrated 48-volt battery with a voltage regulator to protect subsystems from overloading and failure. All components are controlled through the custom PCB in the chassis of the rover. In the event of sudden failure or loss of rover control, an emergency kill switch is located on the back of the rover for quick access. The rover connects to our base station through the use of an AirMax Yagi 900 MHz directional antenna. The antenna is capable of operating up to a range of 1 kilometer and beyond. An onboard NVIDIA Jetson Xavier supports an array of HD cameras that give the operator an excellent view of the rover's surroundings.
BYU's Rover can traverse a wide variety of environments, negotiating extreme grades, stably climbing over rocks, and maneuvering around obstacles. The rover legs are made of aluminum tubing supporting the main body of the rover and distributing the weight while maintaining rigidity. To improve rover traction, our team developed treads out of a polyurethane rubber fiber mix, which was poured into a custom mold and wrapped around the individual wheels. One of our main configurations involves a 6 degree of freedom SCARA-type arm mounted on a vertical power screw for linear actuation. This configuration gives the arm a large workspace, including a vertical range of motion from the ground to 1.2 meters high. Our robotic arm works in Cartesian space using an inverse kinematic software package. The IK method enables intuitive control of the arm, allowing the operator fluid movement without sacrificing precision. It also has the capability to be controlled on a joint-by-joint basis for more specific movement as needed. Some capabilities of the arm include lifting objects up to 5 kilograms in mass, opening and closing a drawer, flipping toggle switches, moving a joystick, plugging in a USB, tightening an Allen head screw, and typing on a keyboard. Our gripper allows the rover to pick up a range of objects up to 15 centimeters wide. Its polyurethane gripping surface is made more compliant with a honeycomb pattern. This means we can securely grasp tools, scientific instruments, supply containers, and even tow a wagon.
To complete tasks safely and efficiently, the rover is mounted with a variety of sensors, such as GPS, a depth-sensing camera, and satellite LiDAR. BYU's rover can drive autonomously to given coordinates with a real-time kinematic GPS system. We use public LiDAR data and a path planning algorithm to find the fastest path to a waypoint while avoiding difficult terrain. Once the path is found, the rover precisely navigates using the RTK system and an unscented Kalman filter to reach the waypoint within 10 centimeters of accuracy. The rover is equipped with 4 cameras and a Z2 that allows us to easily operate well past the view of the control station. The live feeds provided by the cameras give a variety of views, which allow the rover operators to precisely maneuver the rover in any environment. For autonomous traversal, the Z camera houses a built-in magnetometer to provide the rover's heading. Once the rover has completed navigating to a GPS location, it uses the Z's AR detection capabilities to locate AR tags within the vicinity. An LED array on the rover indicates the status of the rover task: green for leg completion, red when autonomous, and blue when in teleoperation.
This year's science team has created a robust module that has 3 life detection tests on board. Each test provides unique information regarding the possibility of life. The module uses burette reagent, flavin, adenine dinucleotide detection, and visual inspection using a microscope to identify extinct and extend life in regolith samples. We have 4 augers on board, 3 for the burette test and the last for sample collection. The burette reagent turns purple in the presence of peptide bonds, which indicates life. Photosensors detect this change and send this information back to the base station for analysis. We use a custom fluorescence microscope to detect any FAD coenzyme present in the sample, which is a strong indication of life. Using generated graphs and confidence intervals from our test data, we can determine the presence of life with above 99% accuracy. As a result of our iterative improvements to the rover design and extensive stress testing, we are confident that we will excel at this year's University Rover Challenge.